Up next is Professor Peter Boyle, head of the Particle Physics Theory Group at the University of Edinburgh and technical director of the SDFC DiRAC computing facility. He has published over 100 papers in the exceedingly computationally intensive field of lattice gauge theory. Professor Boyle has participated in 2 supercomputer development projects. Firstly, the Columbia Enberg-Riken-Brookhaven project to develop the QC-Doc computer with IBM Research. And he led the design of the memory prefetch engine on the IBM Blue Gene Q project with IBM Research, Edinburgh University, and Columbia University. Recently, Professor Boyle has worked with Intel, leading an Intel Parallel Computing Center for QCD co-design, and working with Intel on the Alan Turing Institute. He has 6 patents with IBM and Intel in the area of supercomputing. In this presentation, 4API's and OneCode, Professor Boyle will discuss a performance portability strategy between HIP, Cycle, CUDA, and CPUs, capturing the difference between SIMD and SIMT semantics. Professor Boyle, thank you for joining us today. You may begin.
Thank you. Okay, so I guess one small update that I forgot to give is that I am now jointly Brookhaven National Laboratory and the University of Edinburgh. The title is, of course, a little bit of a play on branding, which I hope people recognize and detect some humor. So I'm going to talk a little bit, as Andrew alluded to the software design challenge, not hardware design challenge of the exascale, and the difficulty of getting not just portability, but performance portability between platforms, which is perhaps significantly harder. I'm going to talk a little bit about original CPU, SIMD, OpenMP background, and then how we've attained portability of our QCD code across a range of architectures, the aim being to target all of the exascale computers that are forthcoming. And then perhaps give just a sort of rambling overview, probably completely disorganized, of where we are in terms of the current hardware platforms that we are anticipating. So GRID is a C++11 high-level data parallel interface for Cartesian grids of various dimensions, to 1, 2, 3, 4, 5 dimensional grids, for example. The principal target is for lattice quantum chromodynamics, but it's been used for all sorts of things. In fact, there's a gentleman in Germany who has recently implemented what I think might be one of the first massively parallel MPI-based quantum computer simulators on top of GRID, using its n-dimensional arrays to store the qubit space in a distributed fashion, which is quite cool. It aims to give performance portability between many exascale architectures. Its multi-core performance and portability has been good for some time, so you can see we're getting 20 to 30% of peak across a range of architectures, and also a decent performance of actually now 1600 gigaflops on Volta, which is comparable to that of the library QUDA that is developed principally by Nvidia developers for QCD. So it's close to best practice now on Nvidia hardware. So I'm going to discuss how I generalize the abstractions to both cover CPU, CUDA, and HIP, Cycle, or OneAPI and OneGo. It also already targets ARM64FX, so the SVE extensions that the Fujitsu computer is using. So if you look at the forthcoming US exascale roadmap, we have Frontier with AMD CPU, AMD GPU, and the HIP programming language. We have Perlmutter with AMD CPUs and the Nvidia GPUs with the CUDA programming language. And we have the Aurora system going in with Intel CPUs and Intel GPUs, none of which are compatible with each other. They're all completely different instruction sets on the GPU side. And the Cycle or OneAPI programming model is what we're targeting. And you'll notice that all three of course have to maintain portability to conventional CPU, multi-core CPU clusters. And you'll note that all of these have different programming models, which is why I'm saying 4APIs. So this is the TETRAC system that we're running in Edinburgh that gets pretty good scaling. Okay, so to start with, just some, on top of the language or software interface diversity, we also have the problem that these computers have fragmented memory systems, so different address spaces for different parts of the code. The problem potentially of data motion unless you're using unified virtual memory, but also the exposure of the splitting of the memory systems into fast, and this is going to be a generic feature in the future because of basic physics and high bandwidth memory and physical packaging and copper wires and their RC delays and so on, that small memories can be fast and close, big memories will be slow and far away. And that exposes performance characteristics that if you do not exploit these or program for these, you will suffer. And a good example of this is the Summit system, where this diagram is supposed to show, you can see the Summit system topologically is like the human brain. It's split into two hemispheres, which are well interconnected in each hemisphere, but go through a slower link between the halves and between the two sockets. And the exposure in this way meant that we actually found out we were better to use NVLink with direct Unix shared memory style addressing between the GPUs to do GPU to GPU transfers within a hemisphere. And that is shown by, I hope you can see my mouse, can you? Well, that transfer over NVLink is being seen in a calculational phase in the profile circled as the higher circle here. Then we have a local face operation and use NPI to go across this X bus because it drives bigger packet sizes and DNA frames over this X bus rather than cache line transfers over the X bus. And in this way, we're already, even within a node, having to differentiate and use hybrid topology, location-aware code that knows where is my GPU within the node. Do I use NVLink with programmed I/O or do I use NPI I/O to get between halves? So this is a good example of the topology-aware code that is having to start to be written to get the most out of these exascale nodes. Okay, so the original multi-core code implemented a number of different SIMD architectures, SSE, AVX, AVX2, AVX512, the BlueGene-Q, Neon for ARM, and ARM SVE. The extension that we had to implement to target exascale coming up, we used a neat programming extension, a neat programming approach that I'll discuss in the next slide, to write single kernels that give high performance, the same source in both SIMD and SIMT architectures, which are, at least superficially, actually pretty different to each other. So the design target is that we have to simultaneously support SIMD with a big vector element processed in each thread's stack. Each thread's local variables are vector local variables, OpenMP and MPI, or go to SIMT, where each thread processes one lane of a SIMD vector, effectively. So the work items in GPUs correspond to a SIMD lane in this underlying SIMD processor, rather than controlling an entire vector or warp the way it would in the CPU SIMD, with offload primitives and NPI. So what we've done does owe homage back to the connection machine and programming tactics that it used. You can actually think of the connection machine where all arrays lived on the accelerator and all scalar variables lived in the host processor as being actually the first accelerator. Okay, so portability, how do we do this? Portability 101, always abstract vendor-specific interfaces and types as an internal to an internal interface in your code, which you can then retarget. So we hide CUDA, x86 intrinsics, NPI behind our own internal vector types, an offload primitive, which can be made to run to an OpenMP loop or run to a CUDA kernel call according to the architecture, and then you can re-implement that abstracted interface to more than one architecture to gain portability. The less talked about second course in portability is performance portability 201, which is that you always abstract your data layouts, because the optimal performance may depend on how you lay out your data, as they depend on vector lengths, cache line sizes, and things like that, and they may affect performance even if they don't affect portability. So the way we do this is we have, in fact in the code we have macros, so we have an accelerator for example, is the key thing, an accelerator barrier, which does a device synchronize, function attributes. You know, everyone who sees CUDA for the first time starts tearing their hair out because they have to mark everything host device in order to call a function on the device. We simply have a vendor neutral function attribute accelerator that then goes to effectively becomes inline on a normal CPU that becomes Nvidia's gobbledygook on Nvidia GPUs and becomes somebody else's gobbledygook on some other thing. But of course you also obviously hit the problem within Nvidia that you cannot add these function attributes to things that live in header files like the standard template library, which I may come back to. So we've abstracted an interface. We have an accelerator for where this is a variadic macro. The ... captures the loop body, and then with this we can expand this macro and create a CUDA kernel call to a lambda function that takes the ... that you feed in, the loop body that you feed in, as the thing that the lambda function does. This, in this sense, is very like the way Cocos or Raja that were mentioned in the previous talk are operating. So there is definitely some convergent evolution. I think several groupings are using advanced C++, capturing loop bodies, sticking them into functors, and then with some kind of lambda process, and then making a kernel call, whether it's to CUDA or to HIP or to SYCL or to an OpenMP, sticking the loop body into an OpenMP loop, according to architecture. So that's a good way to capture to abstract the process of running a parallel loop and manage the mundane mechanics. That said, OpenMP and indeed Cocos don't do very much for changing your data layout in a way that's automatic with the architecture. That's one of the reasons why I cut this myself cleanly. So we have a basic primitive to acceleration, for which we can implement OpenMP, CUDA, HIP, and SYCL versions. So the next step is also that not only does the process of launching the loop have to change with the architecture, but what the loop body actually does has to change with the architecture, because a SIMD loop on a CPU will be processing large vectors, whereas a SIMT loop in a GPU will be processing one element of a large vector if you're writing it optimally. So, in other words, the data layout depends on the architecture. We all remember the good old days, you know, when Bill Gates was viewed as a genius for writing really difficult to write assembly code that was actually really easy compared to the way it is now. We had Scalar Cpus where the registers were scalar registers. You would simply lay out the memory in standard scalar order. The thread would process the data in standard scalar order. There's a one-to-one mapping between memory layout and thread layout. SIMD would stick a vector index in both the memory and thread representation, so each thread processes vectors and they stay in memory in vectors with a one-to-one mapping. SIMT, you really want to have things vectorized in memory so you get coalesced accessing, but each thread or work item in SYCL language processes a scalar representation of that vector data in memory. And you could of course postulate that means there might be a hybrid case where you have a blocking factor between thread and memory, but it's partially vector in thread and bigger vectors in memory or whatever. Who knows? So the way to program this is you clearly need a translation function between memory layout and thread layout and vice versa as you pull stuff to and from memory. So we use operator square brackets to return a whole vector, but operator parentheses returns a scalar image of the memory resident vector object. So this does a translation from struct of array into scalar struct representation of the data and you know that parallel threads within a work group simultaneously do the same translation and coalesce their reads. So that's how we're programming it portably. We write a single kernel that does this. Operator parentheses returns an object whose type changes with the architecture. In a CPU code, it returns a vector object. In a GPU code, it returns a scalar object. And you write the rest of the loop body to use the return type of operator parentheses and the C++ auto keyword to figure out what it's actually operating on. Is this thread operating on a scalar or is it operating on a vector? And because operator parentheses is changing with the architecture, the types inside each loop body change with the architecture too, which is the way to do this in a proper, strongly typed language like C++. Right? So C++ living with the auto keyword is your friend. So a simple example of this is what was a simple linear combination loop, A equals B plus C. That starts to use operator parentheses to drop B, depending on the architecture, to potentially drop B from vector to scalar layout, same for C, add them together, and then insert the result into the current SIMD lane of the vector A. So this is a good way. This code will then give good performance both in a SIMD and a SIMT architecture. So that's a trick that we're doing. Some performance results, Nvidia CUDA. So on Volta, on Summit, we're getting a single GPU, as I said, 1.6 teraflops. It's equivalent, it's within 10% or so, at least, of the code maintained largely by Nvidia developers. It is open source and has academic contributors too. The single node is giving us scaling up to about 6.5 teraflops. We get, Gerardo will be pleased to hear, 46 gigabytes a second out of a possible 50 bidirectional on the dual EDR. And is running now 24/7 essentially, doing calculations towards the anomalous magnetic moment of the muon, which is an experiment that's running at Fermilab. The Nvidia Ampere, we've tried out Booster. We get almost, not quite, but almost double 2.6 teraflops. And a single node with 4 GPUs get 8.9 teraflops. Some mixed news, good news is that this thing has this thing is based in Rome. It has 4 GPUs, 2 Rome sockets, and 4 HDR links. That gives us a phenomenal, 200 plus 200 would be 400 times 4, 1600 gigabits in and out of this node added together. We get delivered 145 out of a possible 200 gigabytes a second running in this quadrille HDR bidirectional host-to-host, achieved after we have done very, very careful process binding to NUMA domains, to GPUs, and to HFIs, so that each MPI rank lives within a quadrant here and have a clear data path to the corresponding HFI. And that is actually, I think, 145 gigabytes a second MPI bandwidth in one node is the highest I've ever heard of to date. We get less than GPU to GPU rather than host to host memory, but hopefully that will improve as it's a work in progress. We have options of using UVM, so we use NVIDIA's page migration, but we also have an optional compile mode that has a homegrown caching interface where we have a software cache for allocations. It's indexed by the CPU pointer. We look it up and you say, is it an entry of this in the GPU, and what is its state? Is it CPU dirty, GPU dirty, accelerator dirty, or is it consistent? And then you translate that to a device pointer for a device loop, etc., and you maintain that cache in a who wrote it last type consistency model. And that I've implemented and is running with an order 1 overhead. So it's using an order 1 hash table to do the lookup, and has an eviction queue that is order 1 access as a linked list. So it doesn't scale with the gigabytes of memory. It doesn't scale with the amount of entries that you have. The cost doesn't scale as you grow the amount of entries it has. We have options to control the caching policy, evict next or evict last, etc. So we can mark priorities for data to retain the right data in the GPU. And I honestly think OpenMP should adopt a similar model rather than having copy in, copy out pragmas under user control. So Intel, SYCL, Aurora, OneAPI. So I've documented the accelerator for macro, and I actually in the same week ported it both to SYCL and to HIP. So each clearly was an effort of order a couple of days. Having got the abstraction right in the first place to capture CUDA, and having made sure the code wasn't peppered liberally throughout the code with instances of CUDA, I essentially went through the code grepping for CUDA and replacing it with accelerator this of my own design, and having eliminated as much CUDA as possible from my code, and replacing it with my own internal interface. I was able to then re-implement that internal interface in a couple of days. So that's good. We have it compiling on SYCL. It has run correctly in one version of the beta. It's not running currently, so we've got stuff to track down. But in principle, we're there with SYCL. On the right here, we have an example of the macro to offload the arbitrary loop through a SYCL primitive. And on the left here, we have the corresponding macro that would expand and give you the right sequence for HIP. Okay, so we have a cut-down version though that does work and runs correctly, and it's giving, for a integrated GPU, this is giving pretty top-notch performance in FP32 and FP64. It's, I think, 30–40% of peak in the double precision compile. So it's doing pretty well. The next, I advertise HIP. So the next case then is the MI50 that was run on in Durham. This is MI100, I believe. I don't know what it's going to be actually, but it's something called Archer. This is going to be the basis for Frontier. This is a Vega, slightly earlier design AMD, but it's the closest we can get to the final Frontier system. So this MI50 has 32 gig of HBM. By all metrics, it looks pretty sensible, and actually by all metrics, it looks pretty comparable to Volta. We can compile and run. We have to delete some bits of the code because of an internal compiler error in the LLVM version in ROCm. But having deleted those bits of the code, it compiles and runs. And we have figures that are not matching Volta, maybe half of Volta. So we get we get pretty good memory bandwidth, 600s, we get maybe 850 in a Volta. The FP32, I quoted 1600 gigaflops in Volta. We're getting less than half of that on the actual code, so there's maybe some things to track down because the memory bandwidth is good, so we're not doing as well in terms of using that memory bandwidth. And double precision is a lot worse. But we have clearly obtained portability with some warts, and Frontier is not available yet, right? So this is preparation for Frontier. So we're making good progress. We have the question of how does Archers compare to Vega nodes, etc. So we're doing quite well, and you can see some example output where we detect 3 Vegas in this node, and we run with a decent memory bandwidth, as I said, in the standard grid benchmarks. Rome. So Rome is, we had a nice day trying some Romes in a hackathon. Rome is quite interesting because it is a multi-chip module. It has essentially a grouping of what I would kind of classify as nearly laptop chips glued together with a big I/O die in a single package. That, I think, connects through something called the Infinity Link. That is, it imposes a slightly different package design that maybe has some more significant benefits from NUMA-aware code than you might otherwise be used to. We had a lot of fun playing with trying to optimize the transfers between NUMA domains within a die and within a node. We wrote a bunch of code, and you can see we could get a huge bidirectional bandwidth intra-node between NUMA domains with puts used in the code, which is what the code originally did actually, and then as it falls out of cache, you get a big drop to the memory bandwidth. So the fundamental cache-to-cache bandwidth is actually doing pretty well in this. So we had some play, the compute only staying within your NUMA domain. We could get up to 3 teraflops out of the 2-socket 128 core Rome node, but we were losing when we were communicating within the node even. So this is NUMA domain to NUMA domain was dragging us down. When we went to 1 rank per socket and 1 NUMA domain per socket with a different BIOS configuration, the compute got a bit slower because the compute memory accesses were across the package, but the intra NUMA domain communications phase was reduced. There was less communication to do, and we won overall with about 2 teraflops per node for the single node calculation, which is pretty good. So what's the conclusion from all this? Well, this headline of 3 teraflops is actually, from 2 devices, is actually pretty impressive. It leaves you with some hope that maybe the processor could strike back. I would actually say this huge drop that you see in the previous slide between intra-node, inter-cache performance and memory-to-memory performance, as you exceed the local 16 megabyte L3 cache size, that edge is clearly quite ferocious and starts to make you think about, couldn't these multi-cores have a much higher bandwidth memory themselves? So I would recall a few illustrious thinkers from our history, such as Richard L. Seitz, the alpha architect, who said it's the memory stupid in the design of the 21264, and note that GPUs have had memory systems that are 10x faster than CPUs, and ask, is the difference really architectural, or is it just that expensive memory is needed, and maybe smaller expensive memory or some differentiation in having fast memory, slow memory, and distance. And I note that dual socket Xeon can have 2,000 cores by Nvidia's counting, because Nvidia tends to count SIMD lanes as a core rather than streaming multiprocessors as a core. Joe Stalin, that great thinker, said quantity, when talking about tanks, quantity has a quality all of its own. And we have to remember that technology gets eaten from below. Artificial methods keep Tesla more expensive than consumer GPUs, right? So really there has to be something that drives down Tesla pricing towards gamer pricing, because that is the nature of competitive market economics. Things get eaten from below. Karl von Clausewitz, the German military strategist who wrote on war, famous, and in addition to talking about war being a continuation of policy by other means, he famously used to talk about Schwerpunkt and acting with the utmost concentration of strength. So really, should we concede compatibility and so on? I would love to see Xeon as an accelerator for Xeon, or Rome with HBM as an accelerator for so some packaging where you have DDR sockets and accelerated sockets where the acceleration is just the memory, and to see that compare, which I don't think anyone has actually done. I know that Fujitsu are including HBM on their computing node, and that makes that an interesting thing to look at, but I don't yet have access to the ARM64FX. And then, of course, that great British thinker, Posh Spice, who said, tell me what you want, what you really, really want. What I really want, as I said, is offload and name only. I would love to see data placement like the SYCL interface, where data motion is controlled through things like buffers to move to and from the accelerated memory system, but simply using that to move into high bandwidth memory in a hierarchical memory system or non-uniform memory system, to have fast memory and slow memory, and accelerate the important loops by marking them up, and having the process that we currently mark up to mark up acceleration for exascale, to mark up this data, mark up data rather than software. Say this data needs to be in a fast place, and execute this loop close to that fast place, independent of actually viewing it as a change of instruction set. And I think that would actually be a kind of more civilized way for scientists to program, because you wouldn't have the software compatibility issues that classic accelerators are not generally able to execute the most flexible possible code. You're trying using a virtual function, for example. So for that reason, I think that offload models and possibly the cycle offload model could automate data placement and motion of code to cores or motion of code to memory systems without necessarily having a change of ISA as you go between these entities. So that's it in summary from me. If there's, I'm done if there's any questions.